The sky over northern Germany was cold and thin on a winter morning in 1943. White vapor trails curled behind engines straining at altitude, where the air was quiet enough to make men feel alone, yet loud enough to tremble through steel. A formation of B-17 flying fortresses moved steadily eastward, their wings locked in disciplined geometry. Dozens of machine guns scanned the horizon. Inside each bomber, young Americans sat at their posts. Gunners, radio operators, pilots, all knowing the enemy would rise to meet them. Below, in concrete bunkers and observation posts, German engineers and Luftwaffe officers tracked the formation. They had seen these aircraft before. They knew the armor. They knew the speed. But what they were still trying to understand was something else entirely. Why did so many German fighters fail to return after attacking them? Flak bursts blossomed beneath the bombers, black smoke folding into the sky. Sirens sounded on airfields, fighters rolled onto runways. The confrontation was inevitable. But in the laboratories and workshops behind the front, another battle was forming, one of measurement, metallurgy, and adaptation. And to understand that battle, we must first understand the world that created the B-17. When the United States entered World War II in December 1941, it arrived with a military doctrine shaped not by desperation, but by theory. The theory that strategic bombing could break a nation's will to fight. American air planners believed that industry, transportation networks, and fuel depots were the heart and arteries of a modern war machine. Destroy them, and the enemy collapses from within. The aircraft chosen to deliver this strategy was the Boeing B-17, a four-engine heavy bomber developed during the late 1930s. It was not the largest or fastest bomber in the world, nor could it carry the heaviest payload. But it was built around two core ideas: survivability and defensive autonomy. The airframe was strengthened to withstand severe damage, and the aircraft bristled with defensive guns, 50-caliber Browning machine guns strategically placed to cover all directions of approach. This philosophy stood in contrast to the British. The Royal Air Force, after suffering heavy losses early in the war, shifted to night bombing, where darkness provided their crews with protection. American commanders, however, insisted on daylight bombing, believing it was the only way to strike targets accurately and cripple German industry in a meaningful way. That decision meant American bomber crews would be visible, traceable, huntable. By 1942, the Luftwaffe had already proven itself one of the most experienced and tactically flexible air forces in the world. Its fighter pilots had gained combat hours over Spain, Poland, France, and the Soviet Union. Many of its aircraft, especially the Messerschmitt Bf-109 and Focke-Wulf Fw-190, were refined through continuous combat-driven improvements. At first, German command believed the B-17 was simply another bomber. A dangerous machine, yes, but one that would fall under concentrated fighter attacks like any other. Early engagement seemed to confirm this. B-17s that flew without escort suffered losses. Bomber crews were shaken. Mission reports described frightening attacks where fast-closing German fighters made slashing passes at high speed. But cracks in German assumptions began to show almost immediately. Luftwaffe pilots reported that closing on a B-17 formation was unlike attacking any previous bomber type. They encountered coordinated streams of heavy machine gun fire coming from all sides. Even when a fighter approached from what was believed to be a blind angle, tracers laced the air where no gun should have been able to reach. Damaged fighters limped home, many trailing oil, coolant, or fuel. Others never returned at all. German airfields began to fill with aircraft riddled by large-caliber rounds, wings punctured, engine cowlings torn open, cockpit armor battered. Mechanics and engineers examined the damage. Reports were filed. Diagrams were drawn. Bomber formations were not simply groups of aircraft flying together. They were interlocking spheres of defensive fire. Each B-17 did not defend itself alone. It defended the aircraft beside it. This innovation, the combat box, meant that an attacking fighter pilot was not challenging one gunner, but dozens. To reach the vulnerable nose, tail, or belly of a bomber, German fighters had to fly into converging arcs of machine gun fire already waiting for them. The Luftwaffe began to understand that this was not a typical aerial opponent. This was a weapons system that forced adaptation. Yet the United States was only increasing production. Thousands of B-17s were rolling off assembly lines in Seattle, Long Beach, and Burbank. Fresh crews were being trained. Convoys crossed the North Atlantic. Airfields in Britain expanded to house entire bomber wings. By the summer of 1943, the 8th Air Force in England had grown from a handful of bombers to a force capable of launching hundreds of aircraft in a single raid. Germany realized this was no temporary threat. This was industrial war in its purest form. Numbers, machines, fuel, steel, ammunition, logistics, all funneling towards the skies above Europe. The B-17 was not meant to win a battle in a day. It was meant to grind an enemy down over time. To understand how German engineers responded, we must first look closer at the aircraft itself, how it was built, how its defenses functioned, and how the Luftwaffe began collecting the information needed to counter it.
To understand why German engineers were so focused on the B-17's defensive abilities, one must first understand how the aircraft was constructed as a self-sustaining fortress in the sky. At its core, the B-17's defense relied on a network of up to 13 .50 caliber M2 Browning machine guns, each operated by trained crewmen who specialized in specific defensive sectors. These guns were positioned to eliminate as many blind spots as possible. Nose guns to counter head-on attacks, top turret to protect the upper hemisphere, ball turret beneath the aircraft covering the vulnerable belly, waist gunners covering both port and starboard, tail guns securing the rear, one of the most common approach points. Later variants added chin turrets, solving the early weakness against frontal assaults. Every gun was connected through an internal intercom communication system, allowing the crew to relay sighting information instantly. Enemy high, 3 o'clock. Bandits closing from below. The aircraft was not a set of guns firing independently. It was a coordinated defensive network, each crew position supporting the others. German pilots who made their first attack runs often underestimated that coordination and paid for it. Meanwhile, German intelligence services were studying the aircraft in detail. Luftwaffe crash recovery teams, known as Bergungskommandos, systematically extracted useful data from downed B-17s across Europe. Whenever a bomber crashed intact enough to examine, engine components, turret systems, ammunition feed mechanisms, and armor plating were cataloged. Captured American crewmen were interviewed, not tortured, questioned. The Luftwaffe understood that fear was not necessary when fatigue, shock, and uncertainty already weakened memory. Pilots, engineers, and intelligence officers asked questions such as, how is turret firing coordinated? Which gun positions are hardest to man under stress? How many degrees of elevation can each turret traverse? What are standard ammo belt lengths? Every fragment of information had value. At the same time, industrial ministries in Germany compiled performance reports comparing .50 BMG round to German aircraft armor. The results were troubling. The American heavy machine gun round could penetrate aluminum airframe plating, coolant radiators, and even armored headrests at combat ranges. The Luftwaffe's earlier light and agile fighters, ideal for attacking slower early war bombers, suddenly faced a machine that could fight back effectively at long range. German engineers began to ask a new question. What must a fighter become to reliably attack a B-17 formation and survive? Air combat reports flowed in from the front. Standard tail chase attacks left fighters exposed to concentrated fire. Side-on passes worked only when perfectly timed. Diving attacks from above increased speed but limited firing windows. Climbing attacks from below risked the deadly ball turret. Luftwaffe pilots, even elite ones with dozens of victories, reported that engaging B-17s felt like attacking a moving fortress protected by invisible firing lines. Many began to prefer head-on attacks, believing the bomber's frontal fire coverage was weaker, a tactic that would soon influence German engineering decisions on reinforced armor, windscreen bulletproofing, and cannon mount positioning. Meanwhile, German aviation design bureaus, particularly those at Messerschmitt, Focke-Wulf, and Junkers, began conducting formal evaluations. Their conclusions showed that the challenge was not only tactical, but technological. If a fighter could not outclimb, outmaneuver, or outrange a B-17 formation, its only advantage would be firepower concentrated in a short firing window. This meant heavier armament, redesigned gun configurations, and eventually new aircraft roles altogether. The confrontation in the sky was shifting from speed and agility to survivability and fire concentration. It was during this period that German engineers realized that the B-17 was not simply a bomber, it was an ecosystem of defensive strategy, testing every assumption the Luftwaffe had built its fighter doctrine upon. The lessons learned would reshape German aircraft design, pilot tactics, and combat formations. To see how deeply those lessons reached, we now examine the issue through multiple angles: tactical, psychological, mechanical, operational, and strategic.
Angle 1. Tactical. The combat box and interlocking fire. The most significant lesson German engineers and tacticians learned came not from the B-17 as an individual aircraft, but from how the Americans flew them. The combat box formation was a geometric structure of bombers arranged in multiple staggered layers of altitude and spacing. From a distance, it looked chaotic, aircraft scattered loosely across the sky, but to a trained observer, it was a three-dimensional fortress of overlapping gun arcs. No bomber defended only itself. Each one protected its neighbor. The top turret of one B-17 covered the blind upper rear sector of the aircraft beside it. The ball turret covered low-angle approaches beneath the formation. The tail guns of a trailing aircraft defended the vulnerable rear of the bomber ahead of it. For a Luftwaffe pilot closing in, the formation was not 30 aircraft. It was hundreds of converging gun barrels focused into any approach vector. German attack doctrine before this point emphasized individual pilot initiative, lone fighters or small sections engaging bombers with freedom to maneuver. Against the B-17 combat box, that autonomy became a disadvantage. A lone fighter darting in and out of the formation was simply torn apart by combined fire. The Luftwaffe had to relearn the tactical principles of mass and timing. This led to the development of coordinated wave attacks, multiple fighters striking simultaneously along a common axis to overwhelm gun coverage. But even when these tactics were executed correctly, losses remained high, forcing Germany to reconsider not only how to attack, but what kind of aircraft was needed to survive the approach. The formation was no longer a target. It was a barrier that required engineering solutions, not only tactical ones. And that realization leads directly into the human dimension, the cost paid by those who confronted it. Angle 2, psychological, the fear of closing distance. Experienced Luftwaffe aces described the first head-on attacks against B-17 formations as entering a storm of metal. The psychological strain on German pilots escalated rapidly with each mission. Unlike dogfights with agile British or Soviet fighters, attacks on B-17s required flying directly into gunfire. Pilot reports described hearing bullets strike the fuselage, seeing plexiglass shatter, and feeling the aircraft shudder under impact. There was no illusion of safety, no room for evasive maneuver until after the firing pass. For many pilots, the moment of psychological breaking did not occur in combat, but in the briefing room, where mission orders were issued. The knowledge that every attack involved confronting an enemy prepared to kill at long range created a quiet, accumulating dread. Unit commanders noted rising stress, reduced volunteer rates for bomber interception units, and growing dependence on veteran pilots to lead attacks. Younger pilots, with fewer flight hours and less confidence, suffered higher fatality rates. Their lack of precision under fire meant they stayed exposed too long, flying into the thickest arcs of defensive rounds. This resulted in an emotional contradiction. The B-17 was not a maneuverable predator. It did not stalk, chase, or surprise, yet it forced fear without motion. German engineers were not blind to this psychological effect. Reports from frontline Gruppenkommandeurs were taken seriously. Aircraft designers knew they were not only modifying machines, they were shaping the emotional survival of pilots. And the core of that fear rested on one element above all: the .50 caliber Browning heavy machine gun. Angle 3, ballistics, the power of the .50 caliber round. Before the B-17 became widespread, most European air combat involved rifle-caliber machine guns, light rounds fired in high volume. These were effective against fabric-covered or lightly armored early war aircraft, but the American .50 BMG round represented an entirely different class of weapon. At typical combat distances of 300 to 600 meters, the .50 caliber could penetrate fighter engine cowling, crack armored pilot headrests, rupture coolant systems and fuel tanks, shatter control linkages and hydraulic lines, disable wing spars and structural ribs. German engineers examining damaged fighters found clean, wide perforations through aluminum panels, sometimes in clusters of 5, 10, or 15 impacts grouped within a few centimeters. Clear evidence of focused, sustained tracking by trained gunners. The B-17's gun mounts allowed continuous rotational aiming, meaning a German fighter could be walked into a gunner's aim even during a diving or climbing pass. The firing arcs were not static, they moved with the attacker. This forced Germany to reconsider two key technical questions. Could their fighters withstand the damage long enough to fire a decisive burst? If not, what changes in armor, fuel tank protection, and cockpit shielding were required? These ballistic findings would reshape entire aircraft designs in the coming months.
But the story does not end with technical reaction alone. The lessons learned now began driving engineering transformation.
Angle 4. Engineering. Reinforced fighters and new armor logic. The B-17 forced German engineers to reconsider how fighter aircraft absorbed damage, not just how they delivered it. Before sustained engagement with American heavy bombers, Luftwaffe fighter design emphasized speed, climb rate, and maneuverability above all else. Aircraft like the Bf-109 were lightweight interceptors built for quick engagements, not prolonged exchanges under heavy return fire. But the .50 caliber defensive belts of the B-17 changed the survival equation. Engineers at Messerschmitt and Focke-Wulf factories began receiving damaged fighters directly from frontline airfields. Inspections revealed repeated patterns: engine coolant lines torn open, pilot head armor dented or pierced, oil radiators shredded. In many cases, pilots did not die from the initial strike. They died because their aircraft could not remain airborne afterward. So changes began. The FW-190 series was the first to shift visibly. Already known for its wide radial engine, it offered greater frontal protection than inline engine fighters. Engineers reinforced the fuel tanks with self-sealing liners, thickened cockpit armor plates, and refined armored windshields to withstand multiple .50 caliber hits. Later variants, such as the FW-190A6 and A8, were explicitly designed with B-17 interception in mind. Meanwhile, the Luftwaffe revived and redefined the concept of the Zerstörer, or destroyer heavy fighter. Aircraft like the Me-410 Hornets carried heavier cannon armament and more armor to survive firing passes. Some variants were equipped with 20mm and 30mm cannons, twin underwing gun pods, Schrage-Musik-style angled guns, specialized gyro gun sights. The purpose was no longer to dogfight. It was to approach, unleash a killing burst in seconds, and escape. German engineers now understood. To defeat the fortress, the attacker had to become more heavily armored and more heavily armed, even at the cost of agility. This was the beginning of an irreversible trade-off. Angle 5. Operational. The evolution of German attack patterns. As understanding of the B-17's fire coverage deepened, the Luftwaffe command shifted focus from aircraft design to attack geometry. Early war interception tactics, tail pursuit, side approach, or shallow diving runs proved increasingly fatal. Pilots attempting to attack from the rear entered overlapping fire arcs from tail, waist, and dorsal gunners. Side passes exposed fighters to multiple tracking guns simultaneously. The Luftwaffe began instructing pilots to execute frontal assault runs, the most dangerous yet most effective angle of attack. Approaching head-on reduced exposure time. The closure rate between aircraft often exceeded 600 to 800 kilometers per hour, meaning both attacker and bomber crews had only seconds to fire. But from this angle, B-17 defensive guns had once been limited. Early variants relied mostly on single flexible nose-mounted guns. German pilots shared stories of brief, deadly windows. A fighter came in fast from high 12 o'clock, fired a 2-second burst into the cockpit or engines, and then rolled away, using speed to escape. Successful strikes could drop a bomber in a flicker of engine flame. But American engineers noticed. By mid-1943, the introduction of the chin turret on the B-17G closed the frontal vulnerability. Twin .50 caliber guns, gyro-stabilized and highly responsive, transformed head-on attacks from an opportunity into a calculated risk. So tactics shifted again. They experimented with vertical attacks, diving from above or climbing from below into blind arcs, firing as they crossed. They also deployed rocket-equipped fighters like the Bf-110 G2-R3 and Me-410, firing salvos to break formation cohesion before close engagement. Yet no matter how tactics evolved, the underlying message was constant. Every approach had a cost. Every second spent near a B-17 meant exposure to heavy defensive fire. This forced Germany into a war of attrition it could not sustain. Angle 6. Strategic. The industrial contest behind the Sky War. Behind the tactics, weapons, and fear, a larger strategic truth was becoming apparent. The air war over Europe was not only about skill, it was about production capacity and endurance. The United States could replace aircraft, engines, and crews at a scale unprecedented in aviation history. Germany, strained by fighting on multiple fronts, could not. Every German pilot lost represented months of irreplaceable training. Every aircraft destroyed consumed aluminum and fuel Germany increasingly lacked. German engineers recognized a painful reality. Even if a perfectly optimized interceptor were built, one with ideal armor, firepower, and speed, the Luftwaffe still needed the fuel, pilots, manufacturing steel, rare alloys, and operational airfields to support it. The B-17 did not just force Germany to redesign fighters, it forced Germany to confront the limits of its own industrial war economy. The fortress in the sky was more than a machine. It was an industrial statement. America could build faster than Germany could destroy. The Luftwaffe could win battles, but it could not win the war of replacement timelines. This realization set the stage for the decisive turning point when the conflict shifted from adaptation to desperation.
By the summer of 1943, the air war over Europe had reached a fever pitch. The U.S. 8th Air Force, now operating from hundreds of airfields across southern England, had matured into a relentless striking arm. Every week, formations of hundreds of B-17s took off in precision waves bound for the heart of the German war economy. Schweinfurt, Regensburg, Bremen, Hamburg, Kiel, and beyond. From the ground, the German people began to look upward not in curiosity, but in dread. The steady hum of four-engine bombers signaled the approach of daylight destruction, a type of warfare that Germany had once inflicted upon others, now returning home with industrial precision. But within the Luftwaffe command structure, a different kind of dread was taking shape. Fighter commanders, maintenance officers, and engineers realized that their entire doctrine, crafted through the Spanish Civil War, Poland, France, and the early Eastern Front, was no longer enough. They were fighting an enemy that refused to yield, flying aircraft that could take damage that should have been fatal, and returning to strike again the very next day. Nowhere was this clash more violently illustrated than in the twin raids of August 17, 1943, the Schweinfurt-Regensburg missions. The day the sky burned. On that morning, 376 B-17 flying fortresses lifted off from England, divided into two task forces. One aimed at Regensburg, home to the Messerschmitt factory producing the Bf-109, the very fighters meant to destroy them. The other targeted Schweinfurt, where Germany's critical ball-bearing plants were located, components essential to every tank, truck, and aircraft engine. The Luftwaffe scrambled over 300 fighters from bases across France and Germany. Among them were Bf-109Gs, FW-190A5s, and several twin-engine Me-110s and Me-410s, bristling with 20mm and 30mm cannon pods. German pilots knew this mission would define the course of the air war, and that many of them would not return. The battle began near Aachen and stretched for hours across central Germany. Bombers flying at 25,000 feet met interceptors rising through layered flak bursts. From the ground, witnesses described the sky as filled with burning metal. Luftwaffe pilots dove in from the sun, unleashing concentrated cannon fire before pulling up sharply. Many hit their marks, engines exploded, wings sheared off, bombers spiraled downward trailing black smoke. But others were shredded before they could escape, struck by waves of .50 caliber tracers from interlocking gun arcs. Inside the bombers, chaos reigned. Oxygen lines burst. Gunners screamed reports over the intercom. The smell of cordite, hydraulic oil, and burning aluminum filled the air. Yet formation discipline held.
rows of aircraft maintaining position even as their comrades burned. German engineers later studied the gun camera footage from these engagements. What they saw was shocking. Many attacking fighters were destroyed before firing a second burst. The combined field of defensive fire was so dense that German pilots described it as flying through a wall. At Regensburg, bombers tore through the Messerschmitt production halls. Assembly lines halted. Dozens of aircraft were destroyed on the ground. At Schweinfurt, explosions ripped through warehouses and ball bearing stockpiles, crippling German mechanical output for months. But victory came at a price. Of the 376 B-17s that took off, 60 were shot down, and over 550 airmen were captured, killed, or missing. Many returning aircraft landed in England so riddled with holes that ground crews called them ghosts in metal. The engineering shock. In Berlin, the Reich Luftfahrtministerium, the German Air Ministry, convened an urgent review. Engineers from Messerschmitt, Focke-Wulf, and Junkers attended. The data was grim. German pilots had fired tens of thousands of cannon shells. Their aim had been precise, yet losses remained staggering. Aircraft damage analysis revealed that B-17s had survived hits that would have annihilated any German plane. Reports cited armored bulkheads shielding critical systems, redundant control cables allowing flight even after partial destruction, self-sealing fuel tanks preventing explosions, gunners maintaining fire discipline despite wounded crewmen. It was not just the machine, it was the system of resilience. To German engineers, this was more than a battlefield observation. It was an existential revelation. The B-17 was the embodiment of industrial durability, a design philosophy Germany could not replicate easily under wartime constraints. Thus began a desperate race. Engineers sought to compensate through increased lethality, designing heavier cannons, greater burst mass, and specialized bomber-destroyer variants. The Me-410B, equipped with twin 30mm Mk108 cannons, was one answer. So was the FW-190A8R8 Sternbach, armored with steel plates and bulletproof glass designed to survive return fire. These aircraft were not nimble, they were battering rams with wings. Luftwaffe squadrons trained to fly them in coordinated head-on waves, using their armor to survive long enough to unleash a single devastating volley. But even as these new fighters reached operational units, another challenge was rising from the horizon, one that would render every German adaptation obsolete. Because soon, the B-17s would no longer fly alone.
By early 1944, the balance of the air war was shifting once again, and this time permanently. The United States had learned the painful lesson of Schweinfurt-Regensburg. Even the indestructible B-17 could not win the skies without escort. Enter the P-51 Mustang, a sleek, long-range fighter powered by the British-designed Rolls-Royce Merlin engine, now mass-produced in America. With drop tanks extending its range deep into Germany, the P-51 changed everything. Before the Mustang, bomber crews flew in tight defensive boxes, relying solely on each other's guns. After the Mustang, they had Angels, fighter escorts that could stay with them all the way to Berlin and back. The Luftwaffe, already bleeding from attrition and fuel shortages, now faced an enemy that could hunt them anywhere. The fortress becomes a spear. The transformation was immediate and devastating. Throughout February and March 1944, the 8th Air Force launched a series of concentrated raids known as Big Week. The targets, Germany's aircraft industry itself. Regensburg, Leipzig, Augsburg, and Brunswick burned under waves of flying fortresses and liberators, escorted by swarms of P-51s, P-47 Thunderbolts, and P-38 Lightnings. The Luftwaffe fighters scrambled, as always, but this time, when they climbed to intercept the bomber streams, they were ambushed. P-51s dove from high altitude, cutting through formation after formation. German pilots were shocked. The Mustangs could outclimb, outturn, and outgun them. The hunters had become the hunted. In a single week, the Luftwaffe lost over 600 fighters, many of them irreplaceable veterans. It wasn't just aircraft, it was experience. The average German pilot's flight hours dropped from 250 to barely 50, while American replacements arrived fully trained and factory fresh. The B-17, once seen as a defensive giant, was now part of an offensive machine, a combined force of endurance, precision, and overwhelming air superiority. A fortress under fire. Still, the B-17s continued to bear the brunt of Germany's fury. One of the haunting moments came during the March 6, 1944 raid on Berlin, the first daylight assault on the Nazi capital. As hundreds of B-17s crossed into Germany, radio chatter filled with tension. Crews knew this was symbolic, the heart of Hitler's empire in broad daylight. Over Magdeburg, the Luftwaffe threw everything it had left: Bf-109Gs, FW-190s, Me-410s, and even a handful of rocket-armed experimental aircraft. The sky became a rolling thunder of explosions. A veteran tail gunner later recalled, "It was like watching the whole world burn in mid-air. You couldn't tell whose smoke was whose. Bombers fell, burning. Fighters spiraled down trailing flames. Yet the formation pressed on." At 12:20 p.m., the first wave dropped its payload on Tempelhof Airfield and Siemens Works. Fires raged across the city. Berliners, who once stood defiantly during RAF night raids, now faced the humiliation of daylight destruction. Out of 700 bombers that launched, 69 were lost. But for the first time, the U.S. Army Air Forces had proven what once seemed impossible: they could strike anywhere in Germany at will. The psychological impact was catastrophic for the Third Reich. German desperation. Within the Luftwaffe High Command, panic was rising. Hermann Göring, humiliated, demanded to know why his fighters could no longer stop the Americans. His famous words echoed through headquarters: "If even one enemy bomber reaches the Ruhr, you can call me Meyer." By 1944, thousands were reaching the Ruhr every week. Desperate, German engineers pushed forward new weapons: the Me-262 jet fighter, the world's first operational jet, capable of speeds no Allied plane could match. It was a technological marvel, but it came too late and in too few numbers. Fuel shortages, political interference, and Allied bombings crippled production. Meanwhile, the FW-190 Stormbuck units tried their suicidal frontal attacks on bomber formations. Some succeeded, ramming or firing at point-blank range, but every engagement further drained the Luftwaffe's strength. The numbers told the real story. By June 1944, Germany could put barely 300 operational fighters in the air to face over 1,000 Allied bombers and escorts. Factories burned, fuel stocks dwindled, and the once proud Luftwaffe was collapsing under the relentless pressure. The fortress ascendant. The B-17, once dismissed by some as slow and outdated, had become a symbol, not of aggression, but of unstoppable endurance. Every rivet, every gun turret, every scarred fuselage told a story of industrial might and human courage. Crews called their planes flying coffins, yet they climbed aboard day after day, knowing that survival was a coin toss. And yet they kept flying. Each mission carved deeper into Germany's industrial heart: synthetic oil plants, rail hubs, munition depots, aircraft factories. Each raid further strangled the German war machine. By the time Allied troops stormed the beaches of Normandy in June 1944, the Luftwaffe was a shadow of its former self. German ground troops looked to the skies and saw not the Iron Cross, but waves of American bombers blotting out the sun. The flying fortress had fulfilled its grim destiny. It had not just survived the air war, it had reshaped it.
When the smoke finally began to clear in 1945, the skies over Europe told the story of an empire undone. For nearly 3 years, the B-17 Flying Fortress had flown through the heart of the Reich, and by the end, Germany's once formidable air defense network lay in ruins. Factories that had produced thousands of Messerschmitts and Focke-Wulfs now stood silent. Assembly lines were twisted wreckage. Airfields that once bristled with fighters were fields of charred metal. The Luftwaffe, once the pride of Hitler's blitzkrieg, had been bled dry. But amid that destruction, German engineers were already doing what they did best: analyzing. Captured bombers, wreckage from crash sites, and the charred remnants of B-17 turrets were gathered and examined in the ruins of laboratories that had once served the Reich's war effort. The question was no longer how to destroy the flying fortress. It was what could be learned from it. German lessons from the B-17. German engineers, especially those from Dornier, Junkers, and Heinkel, meticulously studied the B-17's design. What they discovered was not just American engineering, but a different philosophy of war. They noted the redundancy systems, multiple hydraulic backups, segregated fuel lines, and electrical circuits that allowed a bomber to limp home even after catastrophic damage. To the Germans, whose aircraft often emphasized speed and agility, this was revolutionary. The fortress had been built not to evade death, but to endure it. They studied the Browning 50 caliber machine guns, simple, rugged, interchangeable, and devastating in overlapping fields of fire. German fighters had struggled to approach the bombers from the rear or sides without being shredded. Reports from Luftwaffe test units describe this vividly. No single direction offers safety. The B-17's defensive coverage is total. Even armor placement fascinated them. The B-17's armor wasn't heavy, it was strategic, protecting the pilot, control cables, and oxygen lines. Every ounce was measured against survival odds. The result was an aircraft that could fly home missing half its tail, with engines dead and fuselage torn apart, a machine that defied logic. The iron paradox. But the greatest lesson wasn't mechanical. It was industrial. The B-17 was not the product of a single genius or secret design bureau. It was the outcome of a production philosophy: mass standardization, assembly line repairability, and logistical consistency across thousands of planes. German engineers, who often worked under the pressures of competing ministries and Hitler's personal interference, marveled at how the Americans had made warfare an industrial science. Each B-17 was built with the same parts, the same bolts, the same gunnery systems, meaning any damaged plane could be repaired anywhere in the world using the same toolkit. Germany's aircraft, by contrast, were often unique, hand-fitted machines, marvels of craftsmanship, but nightmares of efficiency. In post-war reports, German designers admitted this difference with reluctant admiration. The Americans did not win because their planes were always better, but because their factories were united. Human lessons. The Luftwaffe pilots who survived also carried lessons of their own. Interrogations by Allied intelligence in 1945 revealed an undercurrent of respect for the B-17 crews. Many German aces described them as machines that fought like men. They spoke of tail gunners who kept firing as their aircraft burned, of bombers flying level through storms of flak when instinct screamed to dive, of radio operators who sent last messages home from flaming compartments. The Americans had designed a fortress, yes, but they had also forged a kind of psychological weapon. Each formation that appeared over Germany was a moving declaration that no distance, no defense, no fear could stop the industrial momentum of the Allies. And yet, for all the respect and lessons learned, those engineers knew what their leaders refused to admit. By the time they understood the fortress, it was already too late. The Luftwaffe was dying, the cities were ashes, and the age of the propeller was giving way to something new, faster, colder, and more technological than anything the world had seen before.
When the war ended in May 1945, much of Germany's scientific and engineering elite found themselves divided between victors. Under Operation Paperclip, dozens of aeronautical experts who had once studied the wreckage of American bombers were now working for the Americans themselves. Others went to the Soviet Union, where they would lay the foundations of Cold War aviation. Among the equipment and research captured by Allied intelligence teams were thousands of pages of technical notes on B-17 defensive systems, structural stress tests, and ballistic damage analysis. These reports would quietly influence the evolution of post-war aircraft design, not just in Germany, but across the entire aviation world. A new kind of warfare. For the Germans who survived, one truth was impossible to ignore. The war had been lost not in the skies alone, but in the factories. In 1943, American plants had built more than 8,600 B-17s, while Germany produced barely 3,000 frontline fighters in the same period. By the final year of the war, American industry could replace a lost bomber faster than Germany could train a single replacement pilot. This disparity defined the air war's outcome. The B-17's endurance and firepower were not isolated triumphs of design. They were symbols of an entire system's superiority. Its turrets, its guns, its repair manuals, everything was part of a machine that could sustain total war indefinitely. German engineers, in post-war interviews, often reflected on this bitterly. We built better fighters, perhaps, but they built the better war. That insight, that logistics and standardization could defeat tactical brilliance, became one of the defining doctrines of post-war military planning worldwide. Echoes in the jet age. Ironically, the very engineers who dissected the B-17's bullet holes would go on to build jet bombers that inherited its lessons. The early ROD 234 jet bomber and the conceptual designs for heavy jet aircraft like the U-28-7 showed traces of the B-17's compartmentalization, segmented systems, modular armor, and reinforced critical zones. In the United States, the lineage was even clearer. Boeing's next generation of bombers, the B-29 Superfortress, then the B-47 Stratojet, and ultimately the B-52 Stratofortress, all carried the genetic code of the B-17. Rugged redundancy, overlapping defensive arcs, and the concept of long-range endurance at altitude. In that sense, the Germans had not only fought against the Flying Fortress, they had helped evolve it. The meticulous notes they left behind, seized by Allied engineers, became reference material for future design decisions. Even Soviet aircraft, like the Tu-4, a reverse-engineered copy of the B-29, owed something indirectly to those wartime German analyses. Legacy of respect. Decades later, former Luftwaffe pilots spoke of the B-17 not with hatred, but with awe. Men who had once fired cannon shells into their aluminum frames described those bombers as iron beasts, machines that refused to die. In 1965, German ace Franz Stigler, who famously spared a crippled B-17 over Germany, reflected on the moment that changed his life. They were men like us. They fought bravely, and their courage deserved respect. That moment, a German fighter escort escorting a shattered B-17 back to the North Sea rather than finishing it off, became one of the most human symbols of the entire air war. It reminded both sides that beneath the armor, the engines, and the flags, the war was fought by men, not machines. The final accounting. By the war's end, more than 12,700 B-17s had been built. Almost 5,000 were lost in combat. Tens of thousands of young men never came home. But their endurance changed history. The B-17's defensive firepower, once dismissed as excessive, had forced the Luftwaffe into an unsustainable battle it could not win.
It taught engineers the power of design simplicity and commanders the value of industrial coordination. For the Germans, the fortress became both a nemesis and a teacher. From its rivets and bullet holes, they learned what total war demanded, not brilliance in design alone, but unity in production, logistics, and resolve. In the cold logic of post-war analysis, the B-17 had not merely defeated Germany in the air, it had defined the very terms of modern warfare. In the end, the B-17 Flying Fortress was more than an aircraft. It was a philosophy made of metal, a statement of how a nation could turn industry into endurance and endurance into victory. German engineers, pilots, and officers, men who had once fought beneath its shadow, came to understand this long after the guns fell silent. What they had faced was not simply American technology, but an entirely different way of waging war, one that prized resilience over elegance, quantity over complexity, and cooperation over individual genius. The fortress represented that shift perfectly. It did not win by speed or maneuver, but by refusing to die. Each mission was an act of defiance, 100 flying machines moving as one, through storms of steel and fire, trusting in the strength of their structure and the discipline of their crews. For the Germans who studied its remains, the B-17 became a paradox, a machine so straightforward, it was almost profound. It taught them that engineering power was not always in invention, but in standardization and simplicity, in the ability to build thousands of identical fortresses, each capable of surviving the unimaginable. In the decades that followed, those lessons spread quietly through the jet age and into the Cold War. The design logic that once terrified the Reich now shaped the aircraft that darted both east and west. And yet, for all its technical legacy, the B-17's true story lies elsewhere, in the human spirit that filled its fuselage, in the gunners who stayed at their posts until the sky went black, in the German pilots who saluted dying enemies as equals, and in the engineers who, after the war, realized that the greatest weapon the Americans ever built wasn't a gun or an engine, but the ability to learn, adapt, and endure. The Flying Fortress had done its duty. It had not just survived history, it had taught it.